I know there is a huge difference kind of a thing right now because there are very less women compared to that of men in quantum. How has that helped you and how has that shaped you? So, is that fine? Like, are there any confusions? Like, we can start otherwise.
Sure.
I'm sorry. I did not hear you.
It's good.
Yeah.
Hear you.
So we are live on YouTube, and at the end, if there are any questions on the questions from the YouTube will be asked by us to you. You can answer those to the participants. And we had a great hackathon. At the end, we also have the award ceremony. It was a great experience. Nafisa, who has done all the work of our hackathon, to be honest, she is not present here as of now.
Oh.
Yeah, we are trying to reach out to her. I don't know, some issue in connecting to her, but we will reach out. Our team will surely reach out to her. And great thanks to her. Kudos to her because it is a huge task and she's managed all these things. So, yeah, this hackathon, the main part of the hackathon is Nafisa because she has organized this. Thanks to her. Um, and yeah, so my name is Nidhi. I'm from India. I'm the Indian ambassador for Girls in Quantum. That's Dhruv from India as well. So I like him to introduce himself as well. And then Arife also is there. She's also from Girls in Quantum team. So I would like her to introduce. Then I will take your name, and then you can introduce yourself and a bit about you being in quantum and how you as a woman have felt and understood about quantum and how others can we can go ahead after that into a bit of discussion as it's Women's Day today, and I'm honored to be with all such great women present here. So yeah, Dhruv, a bit about yourself. Arife, a bit about yourself, then we'll start. Yeah.
Okay. Hi everyone, I'm Dhruv. I'm currently a second year physics major student, and I joined Girls in Quantum a few months back, and it's been an amazing experience. So I didn't know that there was a global organization solely focused on STEM inclusivity, and I am really liking this organization. So it's not only about the girls. So as you can see that I'm also here, but the main idea about the inclusivity, they are doing a very great work. And it has given me an also professional opportunity to collaborate and to talk and to just get out of my bubble. And my mother is my inspiration to make quantum simple. So why I got into this field is that I wanted to make quantum so simple that even she could understand it. So it should not be limited to just super technical physics people. Everyone should be able to understand quantum. So that was my main inspiration. And happy International Women's Day to all of you. You are doing amazing work. Thank you.
All right, let me introduce myself too. I'm Arifanur, and I'm actually a high school student, and I joined Girls in Quantum months ago. And actually, I'm working on the research field in the quantum. Like, I'm leading some projects with the Fujitsu Quantum Simulator Challenge, and then I'm working as a guest advocate. I'm here an ambassador in Girls in Quantum, and I was the judge of the classic track. And actually, I want to tell you that Nafisa is coming right now. So we will continue also with the presentations of the teams.
Yeah, that's great. So I would like Maria, I'm sorry if I pronounce your surname wrong, but Violaris. So I would like you to start. And then, yeah, I mean, I've always, like Dhruv said, I've been going through your work. I've been following your LinkedIn quite a lot. And yeah, you're very inspiring, and it's an honor to speak to you here. So yeah, Maria.
I think you meant Martha, but I guess I'm the one that is supposed to speak. Am I?
Yeah, there's Martha and Maria. So yeah, Martha, you can go ahead.
Okay, no worries. I didn't see
Yeah.
that there was someone else, and since everybody always called me Maria by
Oh,
mistake.
is it? Okay, no worries.
Go ahead,
We can go
Maria.
ahead.
You.
Yeah. Yeah.
Uh, shall I start and then Marta?
Yeah.
Yeah.
As you wish. Yeah.
Cool. Yeah, nice to meet you all, and yeah, nice to be here. Happy International Women's Day. So I guess my introduction is that yeah, well, at the moment I work at Oxford Quantum Circuits in superconducting quantum computing, and I've been kind of doing a mix of quantum research and quantum science communication in the quantum computing field over the past few years. So it kind of yeah, started with my PhD being in the foundations of quantum mechanics, and then I was making videos alongside that with IBM Quantum, and then have kind of brought together quantum computing research and education in my job now at Oxford Quantum Circuits, where I do a mix of both. And yeah, I guess in terms of the I guess being a woman in the field, it does feel a bit like you have a maybe extra responsibility in a way, because you're kind of one of these few women in this kind of new field, especially because it's a new field. It kind of feels like you're at the beginning of what this might look like in the future. But I guess my general philosophy with doing kind of outreach and science communication is that my goal is that I'd like anyone who has an interest in the subject to be able to access it and find out the things that are cool that they might not be aware of exist before. And I hope that through that process, a lot of women that might not initially think of quantum or physics as being something kind of interesting to them for whatever reason, perhaps cultural, or it kind of depends on the context a lot. But yeah, I hope that anyone, including women, kind of find out the things that interest them by kind of creating content and opportunities for those things to find them. So yeah, that's kind of the way I think about it at the moment. And yeah, happy to be connecting with you all.
Yeah. Great. Yeah, I guess we can start with Marta.
Sorry about that. It's just that
No worries. No worries.
people always mistake my name, so I was quite sure it was it was mine.
No worries. No worries.
So nice to be with you all here. I'm here in the behalf of Quandela, and I judged the challenge given by Quandela indeed. I work in the field of quantum since a bit more than 4 years. I started with another startup, and then I moved working for Quandela a bit more than 1 year and a half ago. And mainly I work on quantum algorithms. I did quite a lot of variation on quantum algorithms, actually. And in terms of how it is being a woman in the field, to be honest, it is quite nice because at least in France, there are a lot of women that work in the field. Still not enough, I believe, but there are indeed a lot of great women working in France for quantum. And it's always very inspiring, actually, to work with them and to meet them and to be part of them, of course. So nice to meet you all, and it's great to be here. Thank you.
Yeah, we are happy to have all of you here as well. Ivana, can you go next?
Sure. So
Yeah.
hi everybody. My name is Ivana. I think I am of our judging panel here the only one who's not actively working in the quantum industry at the moment, but I'm a quantum physicist by background. However, I currently work in technology transfer, which means that my job is finding those cool research projects and seeing whether and how we can apply them to the real world. So I'm really excited to see what we will find out about. for this hackathon's results. My background also includes some other quantum startups. For example, if you were participating in QHack that Xanadu was organizing some time ago, that was my team back in the day, and I hope you had a great time, and I hope you had a great time on this one as well. So I'm really looking forward to seeing what we have to find out about today, and really nice meeting everybody. Oh, wait, the experience of being female in the quantum space. I have an excellent example which really hurt my soul. Last year, I was invited to do a talk at a conference about gender in research, specifically in quantum, and one of the PIs at my institute was asking about, I don't understand what gender has to do with quantum research. Why would that be relevant? Why would we even be talking about this? What is there to say? And then I asked him, how many people do you collaborate with? Around 30 to 40, maybe 50. How many of them are women? None. So that stuck with me, and it feels like a piece of experience that repeats itself a lot in the research space. So let's see if we can change it in the future.
I'm sure we will be able to change with all you guys and an inspiration from all you guys here. Um, I get Lindsay, if I'm not wrong. Yeah, am I pronouncing your name correctly? Yeah, you can go
Hi.
next.
Thanks so much. Yeah, it's great to be here with all of you. Yeah, my name's Lindsay Rodenbach. I work at NVIDIA as a developer relations manager on the quantum team. So I manage technical partnerships between academic research groups and NVIDIA's quantum team. My background is in condensed matter physics, but after finishing my PhD, I got into the quantum computing space, and it's been an amazing experience. It is a new field and it's a growing field, and it's really exciting, even though there aren't as many women as there should be and as there will be. I think the fact that it is this new and exciting field, and that we can be this kind of small, empowering group together really drives stronger bonds and makes us, more basically empowered to work together to bring quantum and the love of physics and science to other women. So yeah, it's been an empowering experience in that way. And yeah, I'm really excited to be here with you all today, and yeah, happy International Women's Day.
Yeah, happy International Women's Day to everybody. Next, I guess Danley, if I'm not wrong, right? I'm sorry if I'm pronouncing your names wrong. I'm really sorry.
Me?
Yeah.
Okay. It's an honor to be here right now. I don't know how to say this. I really don't have any trajectory in quantum. This is my first time. I really try to learn what in the most I'm sorry, I don't know how to speak very well in English, but and I'm very nervous. And this is my first time in this type of hackathon also. But I'm really happy to be here. Seeing here these all girls, it for me is an inspiration. I feel really happy here, and I really want to learn more. And all what they said for me is a really very inspired form to want to learn more from quantics, but also be more present in all these kind of projects, in all these kind of hackathons, because it's very important to be a woman in STEM, because we can grow in this kind of type of I don't know how to say this word in English, sesgo. In this type of demand is always in the most part of this type of engineering things or physics or mathematics, but I think the girls are the base of all of that. and I really want to learn about all these incredible girls, and I am very happy to be here again. And I'm so sorry for my speaking in English, but
No worries, no worries. Just to tell that she's our hackathon participant. Um, I guess, Ariana, we can go ahead with you.
Hello, everyone. Super excited actually to be here today. I think it's exciting to be in an environment where we can really we see female being empowered into this field. I'm not a quantum physicist, to be honest, so not even sure if I'm the only one. But I work at QAI Ventures, which is a venture capital focusing and investing only in quantum startups. So I keep being surrounded by men. I'm very excited that right now we have invested in a company where actually the co-founder is a neo mom. So she's traveling in between Brazil and Switzerland with a 3-4 months old. So to me, that is an exciting momentum to see, like a vis-a-vis. That's it. Thank you very much. Excited, and happy International Women's Day to everyone.
Yeah, so Nafisa is here, the main organizer of our hackathon. Thanks to her, because she has organized the whole thing, handled the whole thing. And yeah, she's here. So I officially hand over this to Nafisa. Happy Women's Day, Nafisa.
Okay, thank you, Nidhi, and hi everyone. Happy International Women's Day. And I'm really sorry I'm a little late joining the meeting, and we're, I think, running behind the schedules, but thank you for the wonderful introductions. We were supposed to start with Maria's keynote, and I think that got pushed a little bit because of the introductions, but that's fine, because I'm really happy to hear all the wonderful introductions from everyone, including the participants. So I think if the panelists are
did
done
all of us
introducing
plan
themselves,
to
we can-
introduce ourselves? In that case, I would like to complete it by introducing myself.
Sorry, I
Hi,
didn't catch
am I
that.
audible? So the participants can also introduce themselves?
Oh, yeah, they can. Yeah, go ahead, Mona Lisa. Hi.
Okay, Nafisa, finally, it's a pleasure seeing you. We have been talking back and forth with you. You were amazing. You answered at least 2,000 queries already. So I am one of the participants who also sent her a lot of queries. My name is Mona Lisa, just like the painting. Yes, so that's one name I guess many can pronounce anyway. So I also participated in this hackathon. It was my first time participating in any hackathon. And oh, wow, it was amazing. So, but to come back to the initial question that he asked, how does it feel to be a woman doing quantum in a field known for other particular genders? So this hackathon, I feel, is a very nice answer to that. Like, if I'm not wrong, maybe Nafisa can give more answers. I saw a lot of women taking part here. So this gives me a lot of hope that, yes, the gender ratio might not have been the best in the past, but just by looking at this hackathon, how excited everybody is at various stages of their careers, students, professionals, PhDs, postdoc, everybody collaborating at the same footing. This is incredible to hear. And yes, while there are incredibly few women in the industry right now, this hackathon definitely gives me the hope that it won't be like this for long. So looking forward to that, and happy Women's Day to everyone again. Thank you.
Thank you for the wonderful introduction, Mona Lisa. It really resonates with everyone, I think. And yeah, this hackathon, we have seen a lot of incredible projects from women-led projects. That is one reason why I kind of prompted everyone to mention their team captain names in the beginning, so I could get an idea of how many people were actually leading. I mean, how many women were leading the projects here, and I'm just really happy to see that it's all like a woman-only panel. And I also want to tell all the participants that there is nothing to be scared of, because everyone is going to hear about your projects. And all these women, obviously, they are incredible in what they do, and they're not going to be, be very scary when they judge your projects. But yeah, I'm just gonna quickly pass it to Maria Violaris. I hope she's still here.
Yeah.
Yeah, I can see her. Yeah, so we can probably start with your keynote, and then we can move to the project presentations one by one. That's okay.
Cool. Can I screen share? I've just sent a request. Okay, I think I can do it now. Cool. So I'll just share my slides. And yeah, I think we said a 15-minute talk, but I'll try and keep it quick because I know, yeah, we may be a bit over time. Can you see the slides okay? Yeah, cool. Great. So yeah, as mentioned, happy to be here and to be giving this yeah, kind of keynote talk. I thought it would be fun. Yeah, as I mentioned in the intro, I've kind of been working in the field for a few years now, and I thought it'd be fun to share a few kind of surprises that I've found interesting or surprising over the last few years of working in quantum computing, because yeah, I think it's cool when you're working in such a fast-moving field to kind of see things changing very quickly, and I also just find it quite fun when something changes your perspective of what's happening, or is kind of, yeah, interesting things happening in the field. So that's what I've focused this talk on. And yeah, I already introduced myself, but I just had a couple of slides with a bit about my background. As mentioned, I now work in industry, and I also make content and do research in my spare time. And I have this kind of hybrid role in my job at Oxford Quantum Circuits, doing research and science communication. And I also do kind of my own research and science communication in my spare time. So kind of a hybrid of hybrids. Cool. So to get on to these surprises, the first one that I'm going to highlight is experiments in quantum error correction, which is, yeah, abbreviated to QEC. So the first surprise here that I experienced happened in late 2023, I think in December. There was this paper about the logical quantum processor based on reconfigurable atom arrays in, yeah, December 2023. So this was a neutral atoms paper showing that you can do this error correction process with neutral atoms. And the reason this was a big deal is because kind of until that point, people had been doing experiments with kind of one logical qubit. So I am kind of assuming a bit of quantum computing background here, which I hope everyone's up to speed on, but do let me know if something doesn't make sense. But yeah, so we have the error correction process, and then logical qubits are encoding using lots of physical qubits to encode a qubit in with lower error. And this is going to be essential to do quantum computing with low errors. And yeah, until this point, people had been doing experiments demonstrating this with a small number of qubits, like maybe one logical qubit being demonstrated. And that was kind of the cutting edge of what we could achieve. And it was a big deal whenever someone could do a gate with this logical qubit. And then this paper near the end of 2023 kind of surprised everyone, because they managed to do a load of logical gates with a load of logical qubits. So that's what these numbers are representing. They had like 48 logical qubits, this number of gates. They also managed to do magic gates. So these are like a particularly important resource in quantum computing. And so it was kind of a jump, and it put neutral atoms kind of together with superconducting qubits and trapped ions as kind of the most at the frontiers of the platforms that are pushing the boundaries of quantum computing. So that was one surprise in 2023. But then these experiments have continued to surprise people with new developments. For example, at the end of 2024, there was the Google Willow chip, and this made a big kind of splash in the news as well. And this was just with one logical qubit, but they showed that it kind of passed a certain threshold needed for error correction to work. So essentially, they showed that all of the pieces required for error correction all work out. So it was there's a few pieces that weren't done in this neutral atom experiment, for example. This Google one kind of really showed that everything works. You can reduce the error if you scale up your logical qubit. And so building a quantum computer with low error rate is really possible, like the theory kind of checks out. So that was, maybe a kind of, maybe call it a milestone rather than a surprise, but it was like a big achievement to show that that's possible. So that was number one. And the next one along is also related to quantum error correction. And this is something that it was more of maybe a change in the field generally, but also a kind of surprise to me when I started my job at OQC, was that you can closely design hardware with error correction so that they kind of work together. So before I started my job, when I was kind of just thinking about quantum computing in a more theoretical way, I guess, I kind of saw those as quite separate. Like you have like error correction techniques, and then you've got your hardware. So you try and build qubits that are as good as possible, and then you think about how to use them kind of separately. But there's a whole kind of family of ways that you can actually design these ideas around each other. So I like to use this image where the hand is drawing itself by the artist Escher, because you have this co-design where you design your hardware to work with a particular error correction strategy, and then that feeds back into your design of the hardware. So the strategy that I'm looking at where I work at OQC is with these coaxmons. It's a particular type of superconducting qubit, and essentially what you can do is so these circles are superconducting islands, and a normal qubit would have just one island in the middle instead of these two. But you can kind of engineer it to be different by splitting it into these two, and then that gives different properties to this qubit that are good for error correction. And this is kind of one example of doing this code design, but I've noticed throughout kind of the industry, everyone's kind of doing their own strategy for error correction, and they're very closely tied to the properties of the hardware, both in superconducting and a load of every kind of modality has their own version of this kind of co-design happening. So that's kind of a general trend that I think we've been seeing, this shift more and more to this tight co-designing of the hardware and the error correction. Now, the next one is kind of zooming out a bit more to the trends of the industry, which is that we've seen the rise of kind of roadmaps, especially last year. There were a lot of roadmaps put out of people's pathways to building a quantum computer in the future. And there's also been shifts in the kind of regimes of quantum computing that we think will be useful and for what and when. So in this point, I kind of want to comment on that shift in the regimes that we've been seeing. So there was a term that was coined some years ago called NISQ, so that's noisy intermediate scale quantum. And the idea with NISQ is that it's devices where you have physical qubits that are noisy, and then you try and kind of squeeze out something useful from those physical qubits on the quantum computer. And a good example of very good NISQ devices, maybe the cutting edge of the NISQ devices, are IBM's quantum computers, for example, and they've kind of demonstrated a lot of interesting experiments using lots of physical qubits, kind of doing interesting experiments on those. But there has always kind of been this general question of, well, can we actually get a commercial quantum advantage from a NISQ device, or is it fundamentally too noisy and you have to have error correction to reach the error rates that are low enough to get something useful? And people still kind of debate this question today. So there's this kind of fight in a way between NISQ and then fault tolerance, which is kind of the very far future quantum computer that's resistant to all the errors. And it's been interesting kind of seeing the shift in sentiment in the industry. At first, people were really excited about NISQ. They thought they could get loads of useful things from NISQ. And then it kind of shifted away to saying like, oh, we can only get something useful from fault tolerance. NISQ isn't going to give us anything useful. And then I think it has kind of shifted back a bit to actually maybe we can get something useful from NISQ, but most applications will come out in the fault tolerance area. And yeah, exactly where you put that scale is still a kind of debated question. But yeah, I think now it's kind of maybe somewhere a bit more in the middle than pushed to one side. And then there's a kind of new classification of regimes that has emerged recently, which is to use the term QOP. So if you look at the OQC roadmap, for example, which was put out last year, and other industry roadmaps as well have kind of followed this convention, they've started categorizing the devices in terms of QOPs. So this is like whether you can do millions of quantum operations, so that's megaQOP, or billions is gigaQOP, or trillions is teraQOP. And the idea is that in each of those regimes of more and more kind of reliable quantum operations, you can unlock more and more, a larger and larger range of quantum applications as you kind of reduce the error rate and increase the number of qubits. So that's kind of become the new way that the industry's been discussing kind of the future regimes of quantum computing is in terms of these QOPs. And I did some investigation trying to figure out the origin of the term megaQOP and teraQOP, because it kind of started to be used by a few different people and I wasn't really sure kind of where this idea came from. I ended up finding it by accident when I was reading this paper called A Fault-Tolerant Honeycomb Memory for Quantum Error Correction. It was from 2021, and I noticed in the acknowledgements it acknowledges a Twitter user for suggesting the name teraQOP regime. And it turns out that an anonymous person on Twitter replied to a tweet by Craig Gidney, one of the authors here, asking if anyone had a good idea for a regime where you have 10 to the minus 12 error rate. And someone suggested teraQOP, and then that became, is now the kind of terminology that governments and industry around the world are using. So yeah, that was the third surprise. Now the fourth one is, I guess, zooming out again, looking a bit at the quantum industry and how the dynamics of the industry have been moving. I always find it quite interesting whenever there's like a merger or like a big combining of companies, or one company buys another. And so just to highlight a few interesting things that have happened in the industry. One was the kind of merging of the company Cambridge Quantum with the hardware quantum side of Honeywell. So Cambridge Quantum kind of came from a startup that started in Cambridge in the UK a while ago. And then Honeywell is like a huge company that had a kind of quantum hardware division, and then they separated that out and merged it with the kind of theory software side of Cambridge Quantum to form a new company, Quantinuum, which is now a kind of very large trapped-ion company, has one of the largest trapped-ion efforts. And so that was a kind of interesting theory/software and hardware merger that happened. Then more recently, there was a kind of huge deal that happened last year when the trapped-ion company IonQ, which is kind of came from some Maryland-based researchers, they bought the startup Oxford Ionics, which is a trapped-ion startup that started in Oxford. and spun out from the university here. Yeah, this was like a big acquisition where they Oxford Ionics have some kind of records on the fidelity of their technology and the particular way of scaling. And yeah, I guess it was strong enough that IonQ wanted to acquire that. And then even just this year, there was an interesting acquisition from another quantum company that's been around a long time now. One of the oldest ones is D-Wave. They've traditionally been focused on quantum annealing, which is a bit different to quantum computing. But they've wanted to have a kind of normal gate-based quantum computing effort. And they recently bought a company called QCI, which is a superconducting quantum startup to kind of use their technology for their gate-based quantum computing effort. So that is also an interesting recent development. And just to finish off with the last one, another interesting thing that's happened is that the kind of special source of quantum computing, which is magic states, have traditionally been thought of as being very expensive to implement compared to normal gates. But there was some work done in 2024 showing that actually the resources might be quite similar to doing other gates like control NOT gates. And this has made a big difference to how we think about the resources needed for algorithms, including Shor's algorithm. So this was an important part of a reduction in the estimation for doing Shor's algorithm from 20 million qubits to 1 million qubits. And then there have been more recent estimates of maybe the resources are even lower, but this requires kind of changes to the hardware, and I have a video about that if you're interested. But it's a very subtle, complicated mix of things. But the resources needed for Shor's algorithm have definitely been getting lower over time because of these theoretical developments. So that's all I wanted to present, and look forward to happy to take any questions if there's time, and look forward to hearing more from everyone for the hackathon. Hope there was something interesting for you there.
So if anyone has any questions for Maria, you can go ahead and ask through the chat box, or even you can unmute yourself. That is completely fine as well. I personally want to say that I really enjoyed the fun diagrams that you added in the slides, especially the one Shor's getting closer. I mean, that is very amusing. And I know that earlier the participants had the question whether they should use like PowerPoint slides to present. But yeah, this is one of the reasons you should, because you can get to kind of add these amusing elements to your presentation, and that can really keep the audience engaged. But yeah, if anyone has any questions, please go ahead and ask.
So recently there was a nice survey in which people from all stages in their careers, students, experienced professionals, professors, were asked to make their guesses as to how soon we actually expect to get to the stage of fault-tolerant computing, especially for industrial applications. So may I ask your personal perspective on that?
Mm-hmm. Yeah, I guess what I found interesting about the roadmaps coming out recently and projecting quite far into the future is that we've now got kind of, I guess, predictions or ambitions of building so this TerraQuop regime is kind of the one where you can run Shor's algorithm, where it's kind of at that scale, whereas what you would tend to think of as the fault-tolerant quantum computer. And so at least on this roadmap is kind of 2034. I think if you look at the industry in general, the goal is 2030s at some point to build
this is 2026, and the highest number of logical qubits we have are not more than 150 even. So how optimistic do you feel about scaling up an order of magnitude or two higher? Like, how optimistic do you feel?
Yeah, I think it's interesting because there's definitely a kind of engineering challenge to doing that, and the engineering challenge looks very different for each different strategy. So like for OQC, for example, it looks very different to even another superconducting company that's doing a similar strategy to us because of differences in the implementation. And so I guess if I zoom out and kind of think of the field as a whole, then I see a lot of people putting a lot of effort into a lot of different approaches. And so I'd kind of imagine that at least one of them kind of that you can get through the barriers to scaling in at least one of them. So I guess yeah, I'm optimistic in that sense. I think it's more a question of yeah, how long that will take, and if it's in the industry context, like can the company organize itself sufficiently to solve these problems quickly, and is there something which turns out to be a lot harder than we thought, or I don't know, do advances in AI turn out to help with some aspect of something which we didn't expect, or yeah, I think there's a lot of unknowns, a lot of things that are unexpected, but I am optimistic that any obstacles to scaling up the devices can ultimately be solved, and it's a question of how efficiently we can do that.
If I may ask a follow-up question, do you have any favorite platform, at least for the scaling up part, which you think might be a front runner for now?
Yeah, I mean, the one I'm most excited about is the one I'm working on, which is yeah, kind of looking at these
Superconducting.
Yes, in our particular approach, we're kind of essentially the idea in the future is to kind of keep redesigning this qubit to do kind of smart ways of combining error correction on the hardware level with the outer level. But yeah, I think throughout the industry, there's lots of cool strategies and ideas that people are working on. So I think that's a kind of a fun feature of the industry, is how many different, at least at the moment, the stage that things are at is kind of this exploration of lots of different techniques.
Thank you so much.
I think Lindsay had a question as well.
Yeah, I guess, okay, I'll just quickly ask, as a science communicator, I really loved your presentation, by the way, excellent. That was really fun. As a communicator, so balancing, professional communicator and physicist, what do you think the field as a whole could learn about communicating, like the advantage of quantum computing? Do you think that we're doing a good job? What could be improved? Yeah, I'd love to hear your perspective on that.
Yeah, I think the things that always stick out to me to be improved is maybe when sometimes people make these kind of huge claims that aren't really substantiated, and then that feels kind of like harmful to the field if it's kind of I don't know, the kind of tone of quantum computing is gonna change everything, is gonna replace AI, like we're not gonna need NVIDIA because we're gonna have quantum computing. There's these kind of ideas that people yeah can sometimes find people in the field saying, and I think it ultimately leads to these common myths that there are of maybe that quantum computers kind of speed up every application, or that they do everything in parallel. These kind of oversimplified ways of seeing where quantum advantage comes from. But yeah, but there are lots of kind of there's good science communication happening around it as well. So I think I hope that, like, as time goes on, that kind of persists and spreads amongst common knowledge. And yeah, it's also important to, I suppose there's this balance of not going the other way, in a way that a lot of academics, when explaining quantum computing, can sometimes be overly skeptical of whether we can actually build this thing. And I think that that can kind of come from a more, maybe the academic mindset in general tends to be less ambitious than kind of people working in industry or more entrepreneurial ways of thinking are. So yeah, I guess that tension is difficult to, I guess, balance as a community. But yeah, I guess having good voices out there trying to persuade each other of different views is probably the best thing to have out there.
Yeah, thank you.
Thank you, Maria, for answering all the questions. The answers were wonderful, and I think the participants could also benefit from the answers as well. We are running behind the schedule quite a bit, so I think we should get started with the project presentations. And we have some wonderful teams joining us today, and I'm very excited to start it off with the track winner of the Rigetti Challenge, which is Ecosystem. If the lead is present here, could you please raise your hand?
I'm here.
The sound is very faint. Could you be a little louder?
Sorry, can you hear me?
Yeah, we can hear you. Hi, Ashraf. Thank you for being here.
Hello.
And yeah, thank you for being here. And we're really excited to listen to all the project presentations. And we will start off with your team, which is called Team Ecosystem. And you're the track winner of the Rigetti Challenge. So yeah, I'll just hand over the stage to you. Go ahead, Ashraf, introduce yourself. And
Thank you. Let me share my screen. Is our screen visible? Okay. So hello everyone, happy Women's Day for all girls in quantum and for all women around the globe. I'm Ashraf Bousahi and I'm the leader of the ecosystem team, and we are so happy to present our winning solution at this stage, and we are happy to be here. So just a minute. Okay, so our solution is entitled Polyencoding is all you need, and we are we are 3 happy students that went and present their country and country Algeria and continent Africa in the MIT last month, and we love doing quantum, and we are trying to be among the leaders of the quantum ecosystem in Algeria and in our community. That's why we are called ecosystem. So polyencoding is all you need. The challenge at hand that we had a public dataset present in South Carolina energy grid, and the task was to formulate the maximum power energy section problem into weighted maximum cut, where you have to find the best cut, which is represented here in the red line, where you have so many combinations of possible red lines to cut your graph into 2 zones. And your task is to maximize the sum of the weights that connect the zone A and zone B. So this was the weighted maximum cut problem, and you have so many red lines combinations that you need to find the optimal one that maximize this power energy section metric. So I don't know why. Okay. So the first possible quantum approach that comes to mind is the quantum approximation optimization algorithm, the QAI algorithm. The problem of this approach is that for our simple circuit of simple graph of 180 node graphs, you will need to use 180 qubits. So for each node, you need to map it to a physical qubit, and this is not feasible in the NISQ, noisy intermediate scale quantum devices era. And even the approach that was proposed by the paper of the challenge, that you need to partition your graph into subgraphs and then do multiple quantum approximation or optimization algorithms to you basically will subgraph your graph into subgraphs and then run multiple QAI algorithms on each of them and then combine them at the end. But this will cause us a loss of the global information we have. So we thought that we might do better in our submission, and we went to another approach, which is the polycorrelation encoding. Well, we don't use an Eisen direct mapping of each node into 1 qubit. Instead, we encode the Eisen variable in the sign of expectation value of polywords of weight k. And then we will use a variational quantum eigensolver to minimize the cost function that corresponds to our solution. So basically, each node of this graph, you will map it into a polystring with weight k, where this observable will contain only two poly operators, the x and y or z, and then for each node you will construct this polystring. At the end, you will end up with 180 observable, but this will cause us another problem. So we will need for our graph, for example, 180 measurement round for each of our nodes, and this will cause us a problem. For example, if we run our one measurement round with 10,000 shots, this will be expensive, especially with limited credits and QPU access. So the solution for this was partitioning our observables into 3 commutative sets. So we will basically encode 80 node into a set of polystrings with only the X gates, the X bases, and then the same for the Y gate and the same for Z gates. So instead of, and we know as a quantum property that each of this you can measure so many observables at the same time if they are commutative. So that's why we divide the sets, the observables we have into three bases. And then instead of 180 measurement rounds, we will only need to do 3 measurement rounds. And then we found that with Y is polyencoding all that we need. Instead of mapping each node into a physical qubit, we will drastically rescale the necessity of qubits to an upper bound of m power 1 over k, which is basically, if we choose a compression rate of 2, will be the square root of the number of nodes you have. So in our case, we had 180 nodes, so we only needed 12 qubits to encode our graph. And if we went with a higher k, we will need less qubits, which is so suitable and feasible into the QPU access we had. So after we encode our graph into the expected value of the variational circuit, we train our ansatz, which we will use the efficient SU2 ansatz with 4 repetitions, and then the goal is to minimize the loss function, this complex loss function, using the Adam optimizer with parameter shift rule for analytical gradient descent, which gave great results. And you can see them in our repository. So you basically do a simple VQE optimization loop. You will measure your circuit and then optimize it with the Adam optimizer. And then the output of this circuit, we will have a row circuit, and then we will decode it using the same observables coding we used, and then we will map that cut the produced cut we have through a simple classical post processor to maximize the results we have. So basically, this is the the pipeline we have the graph with 180 nodes, and then we use the encoding with a compression rate of 2 into 3 bases, and then we will run a simple QPU a simple VQE optimization loop to produce the final cut. And the results were very great, and with only a compression rate of 2 and 12 qubits and 4 unstats repetitions. On the QVM simulator we had access to, we was able to reach with deep greedy post-processing, we was able to reach 6,853 in the cut size, where the optimal, the maximum you can mathematically have is 7,465, and even current classical algorithms can't exceed, or the one we tried couldn't exceed the 6,700 ceiling. And for the real QPU experiments, I would like to present to you the website that resumed our project. So basically, when we was announced as winners, we started another hackathon, and we coded this website that resumed all our experiments and all our details. I guess Zeki will share with us the link in the chat. So you can check all our experiments with details. The most important part is our grid optimized with partition nodes and the results we had. And for the QPU experiment, we had this section where we coded this one. When the challenge on the QPU was finding the best qubits that maximize the results. We have tried so many combinations, and the best one was this one. When we have reached on the real QPU 6,600 in the cut size, which is pretty good. Since we have used 12 qubits and a simple readout error mitigation, we didn't have time to try more. We also tried poly-twirling as error correction method, as error mitigation method, and we have tried so many others. You can check the results here, and we have found some interesting qubits and some decent ones on the Anka 3 2D square lattice. And you can see in here that we could reach basically good results on the real QPU, like we see in here in orange. These are the simulator results, and here are the real QPU results. And you can find all the details about our solution in here. And the main goal and the main point we focused on this presentation is that one global optimization picture is much better than dividing your circuit into subgraphs and then do your simple QAI circuit on each one of them and then combine. You will lose the general picture over all your graph. And we proved that our solution is feasible in our QPU, the QPU they had. We pledged into our application that we will try to draft a solution that is based on the QPU and the hardware architecture, and we can say that we kept our promise, and yeah. So I guess this is it. Thank you for your attention, and if you have any questions, we will be happy to answer them. Thank you.
Yeah, so if anyone had any questions for Team Ecosystem, please go ahead and ask. Especially the judges, if you have any questions for him or the team. Okay, so we got one comment from Lindsay. Really great job. Yeah, it's really amazing to see It's really amazing to see your presentation. And I think it makes sense why you got the first place in the Rigetti Challenge. So we will move on to the next team. Wait a minute, what is happening? To the next team, which is also from the Rigetti Challenge, and they actually won the wildcard entry to the presentation today, and that is Team GriddleQ. I hope I pronounced that correctly. It is led by Mona Lisa Singh Roy, and she's here. She's here, right?
Yes.
Yeah. I hope I pronounced that correctly.
Yeah, it's just
GriddleQ.
Grid IQ, because why not?
Grid IQ. Oh, my bad. Yeah, so Grid IQ is going to present next, and I'm really excited about this presentation in particular. Yeah, Mona Lisa, the stage is yours.
Okay, I'll share. Just let me know if you guys see this. Are you guys able to see the screen? Hello?
Yes.
Oh,
yeah, we can see
perfect.
it.
Perfect. So this is Mona Lisa, just like the painting. And I have had the pleasure of joining this hackathon and compete on track A, sponsored by Rigetti. And thanks for this wonderful opportunity, like all of you girls in Quantum, Rigetti, who gave us the shots, and everybody who participated. It was incredible. So let me speak a bit about my team. This is personally my first hackathon. So I did my postdoc in quantum many-body theory, and now I'm a professional algorithm developer, and I'm based in Germany. My team consists of Matteo, also a postdoc in quantum optics and theory. And we also have Saad. He's from Pakistan, and he is actually a power systems engineer. And last but not the least, we have Priyansh from India. He is a student. So throughout this challenge, we had great questions from him. And I think we all got to learn something. So I would love to tell you about what we got to learn. So again, thank you all for giving us a chance to be the wildcard in this entry. Congratulations to the winners. And it's great that you asked us to talk just after them, because I'll explain to you how we thought in an entirely different directions to the winning team. So this is us, and let us take you on a walk through what we did for this beautiful problem. So why is this such a beautiful problem? Because no matter where in the world you are, I know that all members of my team are in different countries. We have time zone issues, but what's common among all of them? We all need powers. None of us can work on our laptop or anything if there was a power outage which was not managed. In addition to the traditional power supplies we have got, now we have the challenge of renewable energy. That's a good thing, right? Why is that a challenge? Because the way the traditional power grids were designed, they like to find the electric consumption to be more or less stable, because no matter how much your usage fluctuates, the electricity they send through the grids is always constant. So any energy you do not use goes back into the grid. So you have to be very careful in designing your networks so that in case of any surges, you don't lose a large part of the network. And that, in a sense, captures why this is such an important problem to tackle. So what we have now is network of electrical grids. The power is coming, the consumption is fluctuating. So we at least need to know what's the maximum power we can send between any two cords. And we need to be prepared for the worst, hoping it doesn't come. So that's where this entire challenge comes to be. So the organizers were kind enough to provide us with the data where we have already a node and all the admittances for the electricity are already given to us as the weights. So a picture like on the right-hand side. From here, what we could formulate was, as suggested in the challenge, to see this as a network. And our task was knowing how much power is being pass through between any two nodes to calculate theoretically how many cuts we can make so that we know what's the maximum power being any boundaries. So essentially, what we want to do is take this entire network and divide it into two parts. Yes, it can lead to islanding. Yes, it can lead to microgrids. But our task here is simply to devise the theoretical maximum power we could send between these edges, which, by the way, is an NP-hard problem. So hence the question that even when we have a Hamiltonian like this, real power grids are a huge problem. How do you feed a 180 qubit size problem into limited hardware? For example, Rigetti has done a great job with Anka 3, 82 qubits, but the problem is 180 size. How do you feed that? So thankfully, these guys already answered that question by reducing the problem into small subgraphs through their Lighthorn methods, extracting the correlation, essentially the quantum information from this circuit. This information goes beyond the weights you're given. And once you have extracted these correlations, feed this to your classical solver. This is brilliant because now you don't need 180 logical qubits. You just need to feed it in chunks. And they have given a very golden baseline, which is their Lighthorn methods. So that got us thinking, wow, if we can use quantum preconditioning to make the problem more digestible to our classical solver, how about we precondition the quantum preconditioning? So that's what we did. Welcome, everyone. What we did in our submission, we went back through the literature of electrical grids, and it really helped that we have a power systems engineer in front of us because we analyzed what is it which electrical engineers already know. That is, not only is it important what your network topology is, but let's look at how they are connected, the degree of connection, the weights they are carrying. And in literature, we found something called the Liouvin method. What does that mean? You try to look at a network and see how strongly it is connected by more number of wires or the total number of weight it can carry, and then try to see, can you make better subgraphs? So yes, that's what we did. So this is the problem which was given to us. 180 nodes, 226 edges. This is the ideal solution. And this is the best solution they reported in the paper. We analyze what is the distribution of the weights, what's the distribution of the connectivity, and use something called spectral embedding. It just tries to concentrate most of your weight locally, and Liouvin method on top of it to construct these kind of different subgraphs. Now, let's look at them a bit more thoroughly. We knew that we had limited number of qubits, okay, 82, but let's work with half of them. So we constrained the sizes of each subgraphs. We calculated the total number of 1 qubit gates and 2 qubit gates each subgraph would need. This way we have around 16 circuits, smaller circuits, which are calculated following how can we best concentrate different weights and connectivities. And then we feed these subgraphs to the normal QAI, which essentially finds the best parameters, the betas and gammas for evolution, gives out the expectation value of combined Zi, Zj. So it's extracting quantum information from here, and just like the paper, feeding back to the classical solver. So did it do something? Yes, but to understand why, you see the blue one is the original weight distribution. And once we use a QAOA to extract the quantum information, this distribution shifts a bit. It's taking into account both the weight and the connectivity to find concentrations of quantum information here. And this is what we use instead of the Lighthorn method described in the paper and feed it to our solver. So now I'll invite Matteo to quickly talk about our pipeline a bit, and then I give you the spoiler. Matteo.
Yes, so thank you very much for your introduction. I am Matteo Piccolini, and as Mona Lisa announced, I'm currently a postdoc at the University of Pavia. And so, yes, basically, we try to build our notebook in the most flexible way. And with this, I mean that we allow the user to define the configuration parameters that needs to be run, and then just press run all cells, and the rest of the notebook will do everything on its own. The configuration parameters that I'm talking about in particular are the type of problem considered, whether type A or type B, the one with 180 nodes. This is the most interesting one, actually. We allow the user also to decide the decomposition technique to use, whether the light cone approach as considered in the reference paper, or the low vein approach discussed by Mona Lisa, or a third approach called the code. We also allow the user to turn off the decomposition technique, and this is particularly useful when you want to run problem A, which does not require decomposition since it has only 21 nodes. We also allow the user to decide whether to use the Rigetti SDK or the IBM SDK, and this is something that we are particularly proud of because it required a super tuned implementation, a very careful implementation, since many parts of the pipeline gets different when you are dealing with the backend by Rigetti or the backend by IBM. They're very different between themselves, so it required attention. Most importantly, we allow the user to decide whether to run an exact simulator, meaning without noise, a noisy simulation only on the IBM SDK, or a quantum hardware implementation. We allow the swap strategy to be turned off and on, and this is something that required time in particular to be implemented, because the swap and swap strategies actually are advanced techniques which try to find the best initial configuration, the best initial mapping between the physical qubits of the specific hardware you're using and the logical qubits. So it's a problem whose output is a map which needs to take into consideration the topology of the specific hardware you're considering. And so we managed to implement this using the IBM hardware. We tried to do that also with the Rigetti hardware, but we had some problems with the way the compiler handles that mapping. So at the end of the day, we managed to implement it only for the IBM SDK. We also allow the user to, if you can go back, please.
Matteo, I will close it now. Thank you so much. So just by following the Matteo...
We also allow to use the GPU, which is something which is available, for example, using Google Colab. We made some run using NVIDIA GPUs, and we allowed the user also to employ another advanced techniques, which is the CVAR cost function evaluation. And these are all techniques which give us a boost with respect to a standard approach.
Thank you so much, Matteo. So with these results, we have reported our comparative runs on both IBM, Rigetti, what we gain by light cone method versus our preconditioning, completely classical in nature. And we have reported all these results, and the MPES number we got is really, really good. But since these results are already reported, I would just like to point out to some silver lining. While yes, all of the methods more or less get the optimum cuts, what can we possibly gain from it? So we tested out different preconditioning, and we found that there is a difference we can still perhaps make, however small, by preconditioning, classically the quantum preconditioning, and then feeding it to the solver, potentially reducing the time. And there is a chance that we can still do well on time as well. So both the solution quality and quantity. So the previous results Matteo collected here are also run on the hardware. These are mostly the simulation results. But what's the take-home message here? Not only did we complete all the pipeline, tested it on hardware, got really good MPES results, most importantly, we found that we can always use better subgraphs here, especially because it's an electric grid problem. We looked at modality and found a better preconditioning for the quantum solver, which feeds to your favorite classical backend. So we are not only hardware agnostic, we are also classical backend agnostic, and provide you a very cheap layer to improve even whatever results you have. So with that, I close our submission, and all of us are very happy to have taken part here. And thank you for choosing us as a wildcard. Happy Women's Day, everyone. I'm happy to take questions.
Thank you very much.
Yeah, that was awesome, Mona Lisa. The whole presentation. I really liked the whole flow of the presentation, but also, like Rigeti judges had mentioned, that this is very well researched. And we have one comment from Lindsay, and she said that very cool to see you considering the SDK preference of the user.
Yes.
Yeah. And if anyone has any questions for Team Grid IQ, please go ahead and ask. You can post it in the comment box as well as unmute yourself. That's completely fine too. Oh yeah, Maria has a question.
Yes, please.
Yeah, just kind of building on this aspect of the SDKs. I was wondering what kind of challenges you found, or was there anything that was particularly different in trying to make it work for both Rigeti and IBM that you might want to comment on?
Matteo, do you want to?
Yeah, sure. Well, most importantly, the compiling and transpilation part was totally different. With IBM, we had a way to assess and build a personalized pass manager, where we employed the swap strategy and the SAT mapper. So this allowed basically tuning of the transpilation process that we didn't manage to perform on the Rigeti hardware. So we allowed the base Rigeti compiler to do the work. And that's one point. And another point always deals with the compilation part that we had to do once before running the classical solver. We employed the Kobila or Kobila, depends on how you want to read it. But basically, the compilation part provided the main difference in the implementation. It's not only a matter of syntax and of specific code words. It's most importantly a question of how you compile your circuit, basically. And you need also to switch from the basis gates of the IBM hardware to the basic gates of the Rigeti hardware. So to do so, we built a certain of translation function which takes the Qiskit built circuit, and once it is done, it transforms it into in such a way that the Rigeti hardware can correctly manipulate and read it too.
Cool, thanks.
You're welcome.
Okay, I have a small announcement to make. So our panelist Ariana Machito, she's about to leave because of the, this is one of the problems with the time zone differences. Not everyone can actually make it, but I'm really grateful to everyone who's here. And I would like Ariana to say a few words before she leaves.
No, I'm just very sorry. Unfortunately, that's the time I had booked for today. It's actually super exciting to see new ideas coming, on the same topics. I wish I had the chance to interact more and to stay longer. Well, thank you, everyone, and all the best on the presentation. And ciao, ciao.
Thank you, Ariana. Ciao.
I'm afraid I have to say something similar to Ariana. It is 1 a.m. where I am at the moment. I will try to stay a bit longer because those two projects that we've seen have been really interesting and wonderful, and great job to everybody, but I might have to leave in the middle of the next one. Sorry.
Yeah, so Ivana is also based in Japan, and that the time zone is really really inconvenient for her. But I'm so incredibly grateful that you still joined and you're here. So yeah, I guess we can move on to the next presentation. That is from track B, and that is by the team called Cashflow. Is the team lead here?
Yes, we are here.
Yeah, we can see you. Hi, Rana.
Hi.
Yeah.
Hi there.
Yeah.
Ziad.
Hi, Ziad. Yeah, we can see you.
Can you see me well?
Yeah.
Okay. Sure, I'll just share my screen. All right. Okay.
Yeah. Hi, everyone. This is Rana Saad from Cashflow, and we are a team of undergraduate students from Egypt, Ziad, Ammar, and Minna, and I. And it's a pleasure for us to be the winners in the finance track, and we will propose you our solution we worked on during the hackathon right now. The problem was mainly about pricing complex financial derivatives. So, why do financial derivatives and swaptions in particular matter in our case? And if you don't have a business or finance background, swaptions basically tells you how a stock price can change over time. So that's why swaptions really matters, because financial institutions need to price swaptions perfectly to manage risk and make informative decisions and keep market stable. So the challenge here, why can't classical models handle this? Deep learning helps sometimes, but it struggles when it's hundreds of correlated financial features, and most of traditional machine learning or deep learning models simplify things too much and this doesn't match with the messy reality of the real market. So the core challenge: how can we accurately model complex financial instrument in a high dimensional and non-linear market environment? So why quantum and why Quandela in this challenge actually? Quantum is known for its feature-based advantage, and as quantum systems naturally operate in exponentially larger space, and Quandela photonic quantum circuits can capture complex nonlinear relationships and project data into richer feature spaces. So in our research journey, we didn't just pick one model and try it. We tested 9 different approaches: classical approach, hybrid approach, and fully quantum approaches. The goal was to find the best optimized, accurate pipeline. So here's what we found across all the models we tried. We started with the classical LSTM as a base model, and we got MSA of 0.34. And then we tried hybrid models like hybrid quantum transformer and hybrid quantum TCN, and tried to change also in the number of photons and circuit design to optimize our pipelines. And through our experiments, error rates went down. But at the end, we decided to build a completely different pipeline. It's a hybrid photonic quantum reservoir, and it blew actually all the results away. It got the least MSA among all the models, and R2 score of 0.998. That is almost perfect. So right now, my teammate Ziad from Cashflow will show you our best pipeline.
Okay, thank you, Rana, for your presentation. All right. So what we tried to do here is we did some research and found out a paper which was published by Dr. Oishik Kar and Dr. Babu from India, which implemented, I think, the called quantum reservoir. And it was actually hinted in the problem description. So what's a quantum reservoir? What's a reservoir in machine learning? Reservoir is not a type of regular classical machine learning models where layers are trained and they are updated regularly. The weights are updated according to the error and the margin of the mistakes. No, it's quite different. What happens here is that the layers are frozen, and just the last or the output layer, it's the one that gets trained. For example, if it's like a camera that captures only the photos and tries to find like patterns or common more patterns across the photos that has been captured. All right, so our pipeline was quite simple. We did the PCA compression for our features were quite large. So just to not make the model confused, and we did our quantum reservoir layers as I said earlier, and also the part that we learned is and implemented is the photonic time delay reservoir, which mimics the action of the regular classical LSTM models of the time forecasting ability to remember the past sequences and the future sequences that's going on to put it into consideration while calculating the possible output of our input data. So here we did a website similar to the ecosystem quantum ecosystem guys. So let's have a look. That's it. All right. So we documented everything that we have done through the process of our project, all the metrics that were rated for each model, and the documentation for our project. If you want to take a look, we'll put it down in the comments. All right. And all the pipelines we followed, all the metrics, all the graphs needed, or anything you would like to say, the architecture, the pipeline of all models are there. And at the end, we put a section that for the sake of trying out different models. So let's, for example, upload the test data that was provided through the hackathon and see how our results will go. So let's this is the data, all right? So let's try any model. For example, here it was chosen the classical LSTM model, and as you can see, because the data was so small, it couldn't catch or recognize the advanced or the complex patterns that was in the data. That's why the photonic architecture was better in addressing such a problem, as Rana said. So as you can see here are the predicted swaption prices according versus the actual swaption prices, and as you can see, there is a margin of error between the two models. It's quite not like quite wrong, but as you can see, there is a big difference between, for example, this value and this value. While, for example, on the other hand, let's try the hybrid photonic quantum reservoir and see our performance and our results. So as you can see here, the swaption number one is quite close to the actual swaption just by quite teeny tiny margin of error. And this shows the potential of the hybrid photonic quantum reservoir and how it performed on such a small or a tiny data. And this just shows the quantum advantage that we have here. So back to the presentation. All right, so and we were very surprised because as Ron said, we tried so many different quantum approaches, and we're surprised that mostly the quantum approaches outperformed the classical approaches by a noticeable amount. This was quite surprising. What we want to do in coming days is that we have to try out on bigger photon numbers or bigger modes to more address the data better, and try to run on a real photonic device if the chance came like this. And yeah, we try to keep it as simple as it could be. And that's it from Team Cashflow. And yeah, thank you for your time, and I'm really happy to hear any questions if you have any. Thank you. All right.
Yeah, you guys did an amazing job. Thank you, Cashflow. So Lindsay had one comment. She said, "Excellent job."
Sure.
Yeah. So if
Thank you so
anyone
much.
has any questions, you can also drop it in the comment section. Yeah, we have to move a little faster because, like I said, we are running behind schedule, unfortunately. So I'll quickly.
Maria does have one.
Okay. So yeah. Maria has a question too. Okay, go ahead.
Yeah, nice presentation. I was just going to ask, so yeah, you focused on this application to the option pricing. I was wondering if you could imagine kind of applying your workflow to like other problems, like either other ones kind of within finance, or have you thought about that at all?
All right. Sorry, I didn't hear that last part. So, can you say it again?
Yeah. So I was wondering if you've thought about applying your workflow to other problems as well.
Yeah, sure. For that's why like that what we thought first. This problem is quite new for us, as we are like CS majors, so we don't have any idea about financial problems. But it really got us so interested in this topic. So yeah, we'd be very open to any other problems, and we would like to like if we can just merge this project into another problem, we'll try to do it. So yeah. It would be a great idea.
Cool, thanks.
Thank you for your answer, Ziad.
Right.
So I guess
Thank
we
you so
can,
much. Sure.
yeah, we can move on to the next team. Team Artemis. Is the team lead here?
Hey, so the team lead is not here. I'm just subbing in for him.
Okay, that's fine. Hi, Tushar. Nice to see you.
Hi. Yes,
Yeah. So yeah, the stage is yours. Go ahead.
Awesome. Can you all see the screen? Okay. Hi, everyone. First of all, thank you for the opportunity to for this hackathon, and of course, happy International Women's Day to all of you. I am Tushar Pandey, part of the team Artemis, and we were solving the classic track C challenge, where we had to do this differential equation and how can we have this harmonic oscillator and how do we simulate it. The team consisted of 3 people, me, Vanshaj, Bindal, and Tanya Keshari. The problem we were trying to solve was actually how do we, first of all, have a toy problem that looks at a differential equation specifically for the harmonic oscillator, and look at all the dials we can tune to either improve the errors or see the difference in pros and cons of how can we change the depth versus how does it affect the accuracy and so on. More precisely, we had let's say a differential equation like dx over dt is mx. And this is a common technique in differential equations where you have, let's say, a higher order differential equation, you convert it into a vector format, and now you have a matrix that resembles that entire higher order differential equation into a simple ordinary differential equation. The problem is, if we want to solve it using this way, since it's easier even classically, the computational bottleneck is multiplying these matrices. So for example, if you have a matrix of size n by n, roughly it takes about order n cubed. And if you really have, let's say, the best matrix multiplication, it's still order n to the power 2.7. What this means is if we want, let's say, an approximation using Taylor expansion, we go to the third or the fourth order, we have to multiply matrices 3-4 times. This scales pretty fast. What that means is maybe with just 100 size n, if you do 7 or 8 multiplications, then you can see how this 100 to the power 10 grows, right? However, in the quantum space, we can actually concentrate and compactify this quite well. In fact, this 100 million rows of operations that would be done classically can be done with just 23 qubits, which means the number or the cross that we have grows from order n cubed to something like order polynomial in logarithmic of n. And I'll talk more about it as to where that is coming from. The idea is you have this matrix representation. The first thing we can try is something called Taylor expansion, where you have the exponential of a matrix, and that becomes, you just expand it. So something like a constant term, then you have matrix times the time with some factorial or constants, and you keep it, it can keep growing for any number of terms. Based on your error threshold, you can pick how many terms do you want. Okay, so classically that all makes sense, but how do I see it in the quantum space? Because for a given unitary, maybe we can apply that directly as a gate. But if you have this summation of different unitaries, how do we do that? And the approach that we took from the paper mentioned in the challenge was you have these ancilla qubits where you can think of it as state 0 of ancilla, you have just that unitary applied once. State 1 of the ancilla, you have the unitary applied twice, and so on. So you entangle the ancilla with these unitaries, which means you have a beautifully entangled state where for each ancilla state, you have all these terms from the Taylor expansion. How does that help? That helps because if that matrix is unitary to begin with, you don't have to do that n cubed multiplication at all. Of course, there's some tuning that you need to do probably based on the size of the system and how easy or difficult it is to decompose the matrix into, let's say, 2 qubit gates and single qubit gates and so on. For harmonic oscillator, actually, it's on the simpler side because the matrix is not just unitary, it's also periodic. And the case that was presented in the paper is actually only for second order differential equation. So with just 4 qubits, we can map it out pretty well. And in this case, if you look at a perfect non-damped version of the harmonic oscillator, then we actually did a period 4 unitary matrix. And what that means is we don't even need to know or have multiple unitaries being applied to the quantum system. So for testing purposes, we actually did a very extensive test on how we can improve the precision, how will it affect the depth, can we make sure that the error is near machine precision, and if that's the case, then how many terms do we need in this Taylor expansion and so on. And what we found was actually something pretty interesting. So a lot of it has nothing really to do with the total size. And for example, let's say with 7 terms from the Taylor expansion, we get some good precision. What this means is we only need 3 ancilla qubits. For the original system, since we worked with a second order differential equation, which translates to just a single qubit structure, with 4 qubits, we can match or actually be better than the machine precision. Furthermore, if we look at the errors mathematically, we will see that if you consider a long enough time, then mathematically the error is going to increase much more with the same number of terms from Taylor expansion, because the error grows with some power of t. which means, let's say from t0 to 1, we can map it very well. It's matching and almost the same as the classical result. But if we go from 0 to 2 pi, which is the period, then we get errors of 68, which doesn't even make sense. So what do? That's where a new innovation idea came in, where after each small time step, we record the final value, and then we put it as the initial value for the next run. And what that does is, for each time step, if the error is, let's say, 1e minus 7, then after 10 time steps, it's still 1e minus 6 at most. And this is what helped us a lot. And I think the best part was to try out all different combinations of possible improvements. So let me show you a little bit of the things that we tried. Sorry that a lot of this is still on Jupyter Notebook, because we are also trying to grow towards a paper. Classically, this is how things should look like. And for quantum, we get the exact same picture. So here we have the quantum and the analytical part, and you can see that it matches pretty well for all the different time steps that we calculated things on. The energy graph is also exactly the same as the classical one. And the important part is, I think, something like this. So as we increase the Taylor order, we can see that the accuracy is really high and the error decays exponentially. Furthermore, we also kind of looked at how does it affect the depth. And you can see that as we increase the Taylor order, then we have some kind of a linear depth increase. So we have this Taylor order convergence, and a lot of this is also mathematically rigorous. We can see that based on the threshold value of your error, you can cut off the Taylor order you want. And this entire architecture is very scalable. For example, we don't really need a lot of new changes to do it all. And just to kind of summarize it at the end, this is the overall error from different parts. And actually, the error from the classic part was kind of the minimum, which is really nice because it was doing in-place changes of encoding and decoding. And we also talked about the scalability from this 2D to multi-dimensional systems. And to me, what was fascinating is actually looking at this graph where the growth is exponential. And then here we can obviously kind of encode that information in logarithmic number of qubits. We did some stress testing as well, where what happens if you have different times where you are simulating it on. And you can see that after some point, quantum seems to just diverge. So, and this is how we had fixed it by this time stepping process. At the very end, maybe I'll just say this, that for small use case, we have already proved that this structure holds well. For larger use cases, we actually aim to do a more mathematically rigorous setup and test out what happens if you can expand this two-dimensional stuff to maybe 3 or 4-dimensional. And in that case, how can we go from there to even potentially fault tolerant at some point? So we have already finished this 4-qubit validation. Maybe within the next week itself, we will be able to do damp oscillators and possibly for non-unitary matrices as well. At some point, we would like to see it on the NIST hardware, how exactly this scales in theory versus on actual quantum systems, and eventually fault tolerant long term. So overall, I think this is an interesting use case, of course, especially because a lot of things actually are based on these differential equations. So if we are able to solve even, let's say, a small part of it, which is this ordinary differential equation, then that already means we can potentially solve lattice quantum field theory and a lot of these really interesting phenomena. Thank you.
Yeah, awesome job, Tushar, with the presentation. We have one comment from Lindsay saying that really great work. I love how thorough you were in considering different resource constraints, error budgets, and stress testing. If anyone has any questions for Tushar, please go ahead. Oh, another thing is that unfortunately, Ivana also had to disconnect because currently it is midnight in Japan and I think around 2 a.m. So she had to leave, and she has said that all teams have shown up really impressive projects, and she was really glad to be here. Okay, I guess with that we can move on to the last team, which is Quantum Warriors. I want to know if the team member from Quantum Warriors is present here.
Yes, we are. I
Yes.
thought.
Yes, we are. Hi, Damli. Hi, Kirtana. Okay, I can see both of you. I guess you can start now.
Mm, it's okay?
Yep.
Okay. Hi everyone. We are Quantum Warriors, a team from Chile, India, and Ecuador. Did you know that today we understand Martian soil better than the first 2 minutes, our own feet? In agriculture, that lack of information has enormous consequences. If you can't measure the soil, you can only guess. And today, modern agriculture is still worked this way, guessing. We still don't know precisely what is happening below the surface. How much water is present, how much nitrogen remains, or how much carbon is stored in the soil. That lack of data has serious environmental consequences. While climate discussion focuses on CO2 and other gases quietly emit across agriculture fields, nitrous oxide. This gas has a global warming potential 273 times greater than CO2. And today, more than 50% of the nitrogen used in agriculture is lost to the environment due to the lack of precise soil data.
This means three things at the same time. First, unnecessary climate emissions. Then billions of dollars is wasted by fertilizers, and then farmers are making decisions with incomplete information. So the current technology have some limitations for solve this problem. Satellites only observe the surface and ground penetrating, radar is struggling in soils with high clay content or then with the salinity or the density. There is literally an invisible data gap between the surface and the subsurface, and that gap forces to the agricultures to operate based on estimation. And we already, as I said, Isidora, we don't want to do that anymore. So we propose a proposal that is quantum roots. That is the solution. Instead of relying on cameras, satellites, or radars, we use something much more fundamental, that is the gravity. So the quantum sensors are based on cold atom interferometry, measure tiny variations in local gravity generated by the mass of the benefit to the soil, In simple terms, we measure how the surface mass pulls on atoms. From these gravitational variations, we can map the surface without digging or disturbing the soil. So how it works, basically, we have inside on the sensors, we use rubidium atoms cooled with lasers. The lasers place these atoms into a special quantum state where they behave like waves traveling along two paths at the same time. Sorry. While the atoms fail freely inside the sensor, the gravity of the source of phase slightly alters those trajectories. So the different masses underground, such as, I don't know, maybe the water, the starbound carbon, or the variations in the soil's density, creates extremely small changes in the local gravitational field. So when the atom trajectories are recombined, they produce an interference patterns that allow us to measure these variations with extraordinary precision. So in other words, we can detect the source of phase structures by measuring teeny changes in the gravity, and as I said before, we don't do this without drilling or digging or starving the soil.
Yeah. So let's continue this. As she said that cold by using how can we implement this? By using cold atom interferometry. So we have to how it works and how we want to implement this. So generally cold atoms, typically rubidium 87, are trapped in a vacuum, cooled to microkelvin temperatures via lasers and released by measuring their free falls using laser pulses is called interferometry. So you can detect minute changes in local gravity level. So it is more helpful. So more water in the soil, it means there is more density. So which gives the gravity signal. So same for carbon and nitrogen. So in this we use magnetic or spectroscopic high sensitivity quantum magnetometers like OPMs or Rydberg atom sensors. So it detects the magnetic susceptibility of soil minerals and presence of organic compounds. So by this, we digitally mapping by mounting these on mobile platform, we can create a 3D density map of the subsurface. So generally by using vacuum chamber, large stainless steel, at titanium or glass atom, these are passed through this. So let's see real-time mapping, how dynamic subsurfaces maps generated as farmers works their field. So recently, we have seen that Massachusetts Institute of Technology that the nitrous oxide produced from fertilizers use can harm certain beneficial soil bacteria. So these bacteria helps plants absorb nutrients and maintain soil health. So the study shows that nitrous oxide can disrupt enzymes in microbes, but preventing some of them growing properly. As fertilizers use increases, this gas may change the balance of the soil. So this could indirectly affect the crop productivity and long-term soil sustainability. So
we don't know what happened with Kertana, but well, let's go with the impact. The impact of this technology basically is twofold. First, from a climate perspective, by knowing exactly where nutrients are in excess or deficit, farmers can reduce unnecessary fertilizers at 20 and 50% of the reduction of this. This directly translates into lower nitrous oxide emissions, like Kertana said before. One of the most powerful greenhouse gases associated with agriculture. Then for the economic model for going on is also an important impact here, because today the agricultural carbon credit market faces a major changes, the verification, and so many current methods for measuring soil the carbon are expensive or destructive or include indirect. So the quantum groups offers a solution based on non-invasive physical measurements of the subsurface, improving the transparency and the relativity in carbon credits generation. Let's go with for the roadmap. Look.
Oh, so now let's see the roadmap, how we implement this in the real world. So our goal is to develop this technology step by step. And the first stage focuses on the developing prototype quantum sensors in experimental agricultural fields. In this phase, the sensors will work alongside existing soil monitoring technologies. This helps us validate the measurements and understand how quantum sensing performs in real farming environments. And in the second stage, these sensors could be integrated into precision agricultural systems and autonomous farm machinery. This would allow farmers to create dynamic maps of what is happening beneath the soil across the entire field in the real time. And our team brings together expertise in physics, data analysis, and computational modeling. This combination allow us to not only to develop the scientific technology, but also to turn it into a practical tool that farmers can actually use. Ultimately, our vision is to take quantum sensing beyond the laboratory and apply it to the one of the biggest challenges of our time. And today we are trying to solve a global climate crisis while still knowing very little about what is happening beneath the feet. Much of agricultural still relies on the estimates and the indirect measurements of soil conditions. So our proposal is simple. Instead of guessing, we start measuring with fundamental precisions. Quantum Roots aims to set a new standard for observing the subsurface environment. By using quantum sensors, we can close the data gap that currently limits sustainable agriculture. Because if we want to cool the planet and secure global food production, we must first understand the system that supports it all, the soil. And this is why we believe it in a time to give the planet something it has never had before, that is quantum roots. So thank you very much, and happy International Women's Day to all everyone present here. Thank you very much.
We are open to questions.
Yeah, that was wonderful. Thank you, Team Quantum Warriors, for your wonderful presentation. And yeah, that brings us to the end of all the presentations that were
Can
lined
I
up for
ask one
today.
question?
Yeah, go ahead.
So guys, I had never thought of anything like this. So I just want to ask, what inspired you? Like, is there any such kind of measurement already performed in scientific literature on any topology for any purpose already?
Izzy, do you want to? In
Check my notes. Thank you. That's a great question. The inspiration comes from two areas of research that already exist. First, quantum gravimeters based on cold atoms interferometry are already used in geophysics to measure extremely small variation on gravity. These instruments have been used to study underground structure, groundwater variation, and even volcanic activity. Second, there is growing research on applying quantum sensor outside the laboratory, especially for air observation and underground mapping. This Sorry, my English is very bad.
No worries. You're great. You're
I
doing
also-
great. You are doing great. But in future, you also want to add that people use this for satellite mapping of certain topology and also some kind of threat detection. That's a good news because people have already thought about using this kind of technology for getting topological information from satellite, and there's huge money being pulled into this. But unfortunately, we need a few more miracles, as Maria mentioned in her keynote address. We probably need few more engineering breakthroughs. But amazing idea. Thank you so much.
Thanks.
Yeah, thank you, Mona Lisa, for that input. That was really insightful as well. I guess that is the, like I said, that is the end of the lineup. And now I have to kind of take the judges that we have to a breakout room, and then we can take a few minutes to decide who is going to get the award from Oxford Quantum Circuits that is being sponsored by Maria Violaris. And yeah, we're just going to make you wait just a few more minutes, and we will be able to announce who is going to get that best overall project title. Okay, wait. Let me see how to do that. Right. Yeah, so I'm going to, yeah, I think it's assigned. Yeah, so you guys have to wait just a little bit before we can know the results.
Izzy, are you there?
Yeah, I am.
Okay, so you are also part of Girls in Quantum, right? Like you form an entire team together with Nafisa.
Yeah, I am.
Okay, thank you so much for making this huge thing happen. It definitely wasn't easy, I'm sure of it. So thank you
I
for making this happen.
Thank you so much. I mean, again, all credit goes to Nafisa because she's planned the whole thing.
Incredible. I mean, she
I'm
applied to
just
so many
helping
people.
her out
Just
in here.
wow.
That's it.
I'm sorry.
Yeah.
Okay.
Our breakout room kicked us out after just 1 minute. Could we have one for maybe a bit longer?
Yeah. Just a
Wait,
minute.
so you guys need me to leave?
No. Nafisa is taking a look on that. So just a minute. Yeah.
So you need to go to that, right?
No. Just a minute. Nafisa is taking care of that. Yeah.
So Lindsay, maybe you introduce also yourself before, but I lost an audio for some portions. May I ask a bit more about you?
Oh, sure. Actually, we have to join the other breakout room real quick, but then I'll be happy to answer when we get back.
Perfect.
Just a minute, Lindsay. I'll just figure that out. Yep. I guess she's joining the breakout room. Let's see.
Oh, she's also a judge. I missed it. Sorry.
Yeah, she is.
This is what happens with horrible earphones.
Yeah, I can understand that. Yeah, she has joined the breakout room. So yeah,
Okay.
that's done. Yeah. So we can just wait, I guess, until then, you participants can just tell me your experience about the hackathon. How did you feel about the hackathon? Till then, we can just.
Amazing. It's so I'm a technology challenged millennial. Like I know the quantum bit quite a bit, the physics bit, but being a part of a time challenge was completely new for me. And it's incredible because I met really cool people out there. It's so great that you guys made sure that make a team. I met people I would have never met otherwise. So, wow, thank you so much for that. And because it happens, right? You talk more with colleagues, you talk more with people who are like you in some ways. But then here we form teams with people we do not know at all. We get to know each other a bit during the competition, and we bring very different kind of expertise, different time zones. And of course, there are disagreements, and still managing to put something together is amazing. I have never had such experience before. So thank you so much.
Yeah. I mean the platform, first of all, Girls in Quantum, and then Nafisa as well. So yeah, you really need to thank Nafisa for that. Because
I
she's
did,
handled
and I will
everything
again.
very, yeah,
So
she's
how did
handled that
you?
all. Sorry?
Perfect. So how did you hear about Girls in Quantum? I found you guys accidentally on LinkedIn.
Oh,
How did
is
you
it?
hear about it?
To be honest, I did find Girls in Quantum on LinkedIn myself. So I was just going through about, and I did a course back 2, 3 years back in quantum computing. And then I
May
was
I
just
ask where?
IBM quantum course, Qubit by Qubit,
Okay.
the coding school. Yeah.
Okay.
Back then it was, I got a scholarship luckily, so
Wow.
I could join the course, and then after that I was just going through and then found out on LinkedIn. Then I joined Girls in Quantum. Like it's been, I guess, 2 years. Yeah, 2.5,
Oh,
I guess.
wow.
Most
Wow.
probably. Yeah. So it's been a great journey being part of Girls in Quantum. The whole team is quite very supportive, and I have met great people. And as you can see, I'm still meeting people who, we follow on LinkedIn, and we're just going through about their work and
Amazing.
quantum and everything. And yeah, I'm still learning. I'm not yet, I'm in still eighth semester. I'm still studying my engineering right now. And
Okay.
yeah, I'm still studying, but yeah, it helps. You need to keep on exploring, and then,
So
yeah.
how is balancing studies and work and meeting, for example, your heroes on a regular basis? How does that feel? How does that work?
Currently I'm in my internship. I'm in my final year. So yeah, I like managing stuff all together. So yeah, I like balancing stuff. I've always been like that in my college as well. I used to handle events in my college, and yeah, so that's been that way. So yeah, it gives me pleasure being a part of all of this, and yeah, of course, learning new things.
So in these 2 years, is there any particular favorite thing you did or your favorite moment,
Um,
something you were the most proud of?
Yeah, I was part of, I've met many people in this journey, so I've definitely found new friends from this. We're all globally connected. We are all in different places. I've not met in person with anybody, but I still know quite many people. So yeah, friendship is one thing, and then yeah, they all have helped in different ways. Like maybe a new topic if I'm seeing or learning, or being a part of a seminar. Like last year, we hosted Q-volution, which was a very big event for us. We connected to many people. So yeah, it's like it goes on. Yeah.
So that's a great life then. Congratulations for
Thank you.
making
Thank
it
you so much.
happen, manifesting and doing it so well. Well done.
Thank you. Thank you so much. Any other participant who would like to share how was your hackathon experience? You can come forward and share that.
Yeah.
Yeah, Kirtana.
Yes. During this hackathon, I had the opportunity to collaborate with participants from different countries, from India, from Latin America. So The time zones are different, but although we came from diverse academic backgrounds and culture, we worked together to exchange ideas and discuss innovative solutions. So the experience was really good. So the exposure in quantum, girls in quantum, it really helpful for women empowerment. So women women empowerment is really needed nowadays. Why? Because um, in every sector, women are like quantum computing, semiconductor industries, manufacturing, or artificial intelligence. Women are empowering, but there should be some encouragement to the women. So I thought Girls in Quantum is the best platform. So I was really grateful to have this opportunity to participate this in hackathon.
Yeah,
And once
it's
again,
a
happy
pleasure.
International Women's Day.
Same to you. Same to you.
Yeah.
Anybody else? Yeah, please go ahead. Say it. If
I'd
I'm
just like to point out how great this hackathon was, and actually to compete among like different nationalities and around the globe. So it was a great opportunity to do so, and yeah, and it actually inspired me to do more ideas or more projects after this hackathon, hopefully, inshallah. And yeah, and I would like to thank all the organizing team for their efforts. And yeah, that's it.
You're welcome. You're welcome. I guess then we'll just wait a bit for the results. Yeah, all the best, everybody. So till then, there are many girls and women present here. So, on the honor of Women's Day, like, would you like to share an experience which you've, had regarding your work? Being a woman in quantum or something like that? You can just discuss something.
It looks like I'm talking the most. I do hope somebody else speaks
No,
up.
no worries. I mean, you are quite interactive, and I mean, that is working a lot for me as well. So, yeah.
Okay, so one thing is, it's really true what you guys also started with. if you consider streams like, I don't know, biology or chemistry. So I'm originally from a city called Calcutta, though I grew up all over India. So at least in Calcutta, I have seen that in biology and chemistry, somehow the number of women is like 50-50. But when it comes to physics and maths, and maybe, I don't know, some branches of engineering like mechanical engineering or stuff, somehow there is a very stark difference in the ratio of the number of women studying versus men. And this ratio keeps getting worse as you go higher up in the career. Like, you see still a handful of women studying physics. Sorry, I
to
think.
interrupt.
I guess
No,
they're
Sorry to
back
no,
in. Sorry. We were just discussing about girls in fields of engineering and stuff. So it's on the day till y'all had to come. So I guess she can just wrap it up in 2 minutes and then we can go ahead with
30
the
seconds.
Yeah, sure. Yeah.
A handful
Very
of
eager to hear it.
women you see in physics and maths at bachelor's, that handful becomes fewer in master's and probably one for PhD. So there is this trend I somehow feel, and this trend is not common to South Asia. I have seen this in Europe and the States as well. So whatever is happening is somewhat universal. I wonder if it's the societal rule or is it some kind of invisible expectation? Something is happening, but it's really good to see that young people like you and many others are getting this nice exposure at an early stage and killing it. So maybe we can stop that number reducing as you go higher in the career. Maybe it will at least flatten, if not increase. But I really look forward to that. That's all. Thanks.
Yeah, thank you. Nafisa, over to you.
I wish I was there to actually hear the whole thing. That sounded really intriguing. But we have the winner, and Lindsay, Maria, and Marta spent quite a lot of time discussing the projects, and then they came to the conclusion that the best overall project award goes to Team Grid IQ. I don't know how to do the celebration reaction, but yeah, they have the best overall project title, and they're going to get the QPU access from Oxford Quantum Circuits. So yeah, congratulations, Grid IQ, and congratulations to every other track winner as well, because in the end of the day, you guys are track winners. Yeah, getting a lot of reactions here. So Maria, do you have a few more words to say since the award is coming from Oxford Quantum Circuits? Would you like to say a few more words?
Sure. Yeah, congrats, Grid IQ. Yeah, we really liked your presentation and we thought it was really well-rounded in terms of the categories we were looking at, with kind of impact and feasibility and then communication and creativity. But yeah, more generally, we really enjoyed everyone's presentations. As I said, we were discussing a lot on all the different aspects, and everyone had different aspects that we thought you did really well. So yeah, congrats to everyone on being involved in this and for your hard work on it. And yeah, I hope that the winning team, so we've got some access to OQC hardware, to the QPUs that we have. So I hope you can use that to do something interesting, building on the cool work that you've been doing. And yeah, look forward to.
We fully intend to. Thank you so much for making it possible with the hardware support. We really are onto something even better than what we presented, but we really needed this hardware support to see it through. Thank you so much for giving us that support. Thank you so much, Maria.
Yeah, that's great. And yeah,
thank you so much.
Thank you so much
for your presentations.
Priyansh, are you there?
That's all from me. Thanks.
Yeah, so I'd like to also pass it to Lindsay and Marta to say a few words about Team Grid IQ, and then we can finally wrap up the session.
Sure. Yeah. No, I mean, I want to echo everything that Maria said, and I thought that all the teams did a really excellent job. We were we had fun, discussing everyone and all of your projects, and you all did amazing work. It always blows my mind what people are able to accomplish in these hackathons, and how creative everyone is, and it makes me just so even more excited about where this field is going and all of the amazing people working in it. So yeah, just really great work, everyone.
On my side, I want to say congratulations, and really everybody did an amazing job. It was very hard to decide on the best team, to be honest. We wanted everyone to win, but unfortunately it's not possible. So congratulations to the winning team, but also congratulations to all the others. And once again, as Leslie said, it's amazing what you can accomplish during the hackathons. It's really unbelievable almost. So congratulations to everyone.
Thanks a lot again.
Thank you.
Yeah, so thank you all. Congratulations to everyone. For the last time, I'm just going to repeat the names of the winning teams. And yes, everyone, all the track winners are going to get their rewards, their allocated rewards and certificates and all that. It's just that Grid IQ will get an extra award from Oxford Quantum Circuits for their amazing work. So yeah, all the teams from track A, it was Ecosystem. Congratulations. And then Grid IQ, who won the wildcard entry to the grand finale. And then for track B, we had Cash Flow. Congratulations. For track C, we had Artemis. Congratulations to you guys as well. And finally, we had Quantum Warriors, who did a great job too. Congratulations to all. And thank you again for joining and participating in the hackathon. It would not have been possible without your support and your participation. So yeah, happy International Women's Day, everyone.
Thank you so much. See you, and thank you for all the hard work, Nafisa. You killed it. Wow. Amazing. Thank you so much for helping all of us make new friends. And this was amazing. No words can suffice. Thank you so
I
much.
would also like to, thank you for that. But also another teammate from GIQ who has worked quite a bit. That is Arife. Arife is here with us too. Thank you, Arife, for all the work. I think I would have gone insane if she weren't here. And Nidhi and Dhruv and Felipe and all. Thank you so much. Again, I had a lot of fun as well. So yeah, really cherish this experience.
Thank you. See you guys then.
Goodbye.
Bye-bye.
Great day. Bye-bye.
Bye. Have a nice day.